Hi, welcome to another video in my series on centers of mass. Now, you might like to try this one. This is where we have a uniform lambda made up of a rectangle and a triangle here. And in an earlier video, I showed you how you go about finding the center of mass for composite shapes. So you might like to have a go at this one. Just pause the video, come back when ready, and I'll run through the solution for you. Okay, welcome back if you had a go. So, what would be the first thing I would do? Well, there's certainly no axis of symmetry here, so I'd want to set up an X and a Y axis, and you can set them up wherever you like, but generally it's a good idea to set them out on the outer edges of your shape. So I'm going to put my X-axis in along here, and I'm going to have a Y-axis up through here. So we end up with our origin down here. Need to put the centers of mass now of each of these two shapes. So we know that they're uniform, so the center of mass of the rectangle here is going to be in the middle. And that will have coordinates of 2 across, 5 up. So we'll just mark that in as 2, 5. Now the center of mass of the triangle, okay, is going to be at the intersection of the medians. As I showed you in an earlier video, it's going to be somewhere around there. But you can work out the coordinates of the center of mass by doing the mean of the X and Y coordinates of the vertices. And if you're unsure of that, again, I did that in an earlier video. So we need to get these coordinates then. So what's the coordinate of this vertex here? Well, it's clearly going to be 4 units across, none up. 4, 0 then for that one. For this vertex, it's going to be 6 units across, the 4 and the 2. So it's going to be 6, 0. And for this one here, it's going to be 4 units across and then 4 units up. So that will be at 4, 4. So if we're going to work out the coordinates of the center of mass here for this triangular lambda, then we need to consider that triangle. So we'll just have a subtitle here. So if these coordinates then are x bar, y bar, we can say that x bar, y bar is going to be equal to the mean then of the x coordinates and the y coordinates. So it'll be 4 plus 4 plus 6 all divided by 3. And that will be x bar. And then for y bar, we've got 0 plus 4 plus 0 all divided by 3. 0 plus 4 plus 0 all divided by 3. And if we work that out, we've got 14 thirds. And for y bar, we've got 4 thirds. Okay, so that's the coordinates then of the center of mass of that triangular lambda here. Let's just mark that in now as 14 thirds and 4 thirds. Now that we've got the center of mass of each of these lambdas, we need to work out what the mass would be of each of them. And to do that, what we're going to do is let the mass per unit area equals some constant, and that constant can be anything you like. I'm going to call it m, and that means that when it comes to the mass of the rectangle here, we've just got to work out its area, which is 10 times 4, 40 centimeter squares, multiply it by the m, and you've got 40m for that mass. As for the triangle here, we just got to do the base times the height. The height here is 4 units, and divide by 2. So we've got 2 times 4, which is 8, divided by 2 is 4. Times it by m now, and we've got 4m for that mass there. So where is the center of mass going to be now for the whole lambda? the composite shape? Well, it's going to be somewhere between these particles. I'm just going to stick it here, say. We'll call it C if you like. And it's got coordinates x bar, y bar. Now, the mass we can assume centered at C is going to be the total then of these two masses, 40m and 4m. So we've got a total mass here of 44m. Just squeeze that in there. So all we need to do now is take moments in the usual way about the x and y axis. And so our equation for that, if we consider the whole lambda, let's just mark in another subtitle here, consider the lambda. If we do that, we're going to have the total mass, 44m, multiplied by x bar, y bar, is equal to the moments of each of these individual masses about the x and y axis. So it's going to be 40m multiplied by the column vector 25, and then plus the moment produced from the particle here, 4m, which is going to be 4m multiplied by 14 thirds and 4 thirds. So we'll go 14 thirds and 4 thirds. Now the m's cancel, so we can take those out. They're in each term. And if we work this out now, we've got 44 multiplied by x bar, y bar equals, and if you do 40 times 2 plus 4 times 14 thirds, on the top you end up with 296 thirds. And if you do 40 times 5 plus 4 times 4 thirds, on the bottom you end up with 616 thirds. Now all we need to do is divide these two values by 44 to get x bar, y bar. And I'll write it as a coordinate now. X bar, y bar would equal, so 296 thirds divided by 44 ends up as 77 over 33. And as for y bar, 616 over 3 divided by 44 gives us 14 thirds. Okay, so that gives us then the centre of mass, the coordinates of the centre of mass. And obviously, if it asks you for the distances to this side here and this side here, this would be the answer. But you might have to make adjustments if they wanted it from some other side. Okay? But I hope that's given you some idea then how to work out the centre of mass for this composite shape.